Swayam Prabha. Digital India. Educated India.
Good morning, everyone, and welcome to this another session in our series of video lectures on Introduction to Aerodynamics. In today's session, we will talk about a very generic tool. It is a very generic and a very powerful tool known as the Buckingham's Pi Theorem. It's also known by other names such as dimensional analysis, similitude. You will see that it results in the formation of something known as the pi groups, which are non-dimensional groups that are very important for a given physical problem. So essentially, in any physical problem, you have a relationship between variables. For example, the force on a wing is influenced by the velocity of flow around the wing, by the density of that flow around the wing, the maybe the angle of attack, the geometry of the wing, or at least the chord length of the wing, etc. So we will see that there is an interdependency between all these parameters, and from these parameters that influence the problem, you can combine some of these parameters and get things known as the pi groups or the non-dimensional groups that have significant impact on the way the flow problem or the the dependency of one parameter on the other, etc., can be obtained as the dependency between these non-dimensional groups. And we will see why we, instead of working with the parameters themselves, so instead of working with force and say the velocity or force and the chord length or something of this sort, we will, in engineering and in many of these physical systems analysis, we have this tendency to work with these non-dimensional groups, and we will see why that is the case. Now, so we have seen, let me switch on to my my screen, and by now you have seen many times these plots. We do CL versus alpha, the angle of attack. We have shown CD versus CL or even alpha, CD versus the Mach number, etc. Now you see, we could have just shown the drag versus some other parameter. For example, drag versus. So you will often see these plots, the non-dimensionalized plots. Okay, so this is drag divided by half rho u square times s, where s is the reference area, in this case the planform area, and we get this CD plot. Remember that C small d is essentially for the airfoil, okay, or for the infinite wing. So here we are showing that the drag coefficient for the airfoil as a function of alpha or CL. And you see that we are saying that, okay, at a given Mach number and a given Reynolds number, as you change your angle of attack or eventually your CL, because CL is a function of alpha, as you see here, your CD has some variation. But you see, interestingly, we are not talking about the dimensional variables against each other. So you will rarely see, of course, in an experimental work, you might be computing drag versus the, say, the free stream velocity, holding some parameters constant. But eventually, when you report experimental results, it is always represented. I mean, there is a reason for that. It's most often, or it is usefully represented. So if you represent it in these kind of non-dimensional axis, there is some, like advantage in reporting these things in this fashion using non-dimensional variables. So you plot, one non-dimensional variable against another non-dimensional variable, holding the other non-dimensional variables constant. And of course, how do you get the non-dimensional variables? Are some of these non-dimensional variables physically relevant or not? Are there more than what you see non-dimensional variables in a problem? So these things are part and parcel of the Buckingham's Pi theorem, dimensional analysis and similitude. And I must say at this point that eventually, we will also see another approach where we start with a governing equation, popularly ODE or a PDE. For example, you can start with the Navier-Stokes, or you can start with the Euler's equation, and you apply a similar kind of thing. Okay, we say normalization and non-dimensionalization. When you do that, some of these non-dimensional groups also come out of the PDEs, or the ODEs. And there, these are not only non-dimensional groups, but these are groups that have important effects on the problem on hand. So essentially, see, Navier-Stokes applies to flow over a small cylinder or a large aircraft or a small wing, large wing. Now the question is, how do we, you run an experiment on a small wing cross section? How is it relevant for a large wing? Exposed to a very high, comparative wind speed, etc. So we will see that when you start with these PDEs or ODEs and you normalize and non-dimensionalize, what happens is the equation becomes one in the normalized variables, and some of these non-dimensional groups come as coefficients in front of various terms. And we will see that things like Mach number, Reynolds numbers, Prandtl number, these non-dimensional groups come out from that treatment of the governing equations. On the other hand, Buckingham's Pi theorem is a simpler approach of collecting these non-dimensionalized groups which are of importance to a physical problem, but not necessarily these non-dimensional groups have the connotation of physically relevant parameters. So for example, Reynolds number, Mach number, Prandtl number, these things fall out from the second approach, where you start with normalizing and non-dimensionalizing the terms in a PDE or ODE, or we say the governing equations. On the other hand, from Buckingham's Pi theorem, you get the pi groups. You can, if you kind of know that these are the physically relevant pi groups, you can, by the choice of the repeating variables, etc., you can generate pi groups that are eventually, like a drag coefficient, Reynolds number, etc. But there is no guarantee that given a random choice of these repeating variables, we will see what these repeating variables mean. There is no guarantee that for any choice of repeating variables, the non-dimensional groups that we get will be, things that are physically relevant to these fluid problems. But nonetheless, you can rearrange these non-dimensional or the pi groups that you get from Buckingham's Pi theorem approach. You can rearrange them and eventually get to physically relevant pi groups. Okay, so this is just a basic introduction. So once again, instead of plotting, say, force versus velocity, force versus, say, the viscosity, we have this approach of plotting non-dimensional variables against one another, and we will see why we do that and the significance of it and how it is done. Now here, let's start with a very simple problem. So we have a cylinder. It's a fluid mechanics problem. So we have a cylinder of diameter d exposed to a flow with velocity v infinity, and the density is rho infinity, viscosity is mu infinity, and we are interested in seeing the force, that is, or the drag force. Remember that this is the force along the relative wind direction. Okay, so we are interested in finding the drag force. Now, this method of this Buckingham Pi theorem, although attributed to Buckingham 1914, has been discussed by other researchers, famously Lord Rayleigh, in his book The Theory of Sound, discusses it as a part of method of dimensions. Vashi in 1892 has talked about dimensional analysis and something similar to this. Ryabowczyński also has indicated has done some work independently as early as 1911. However, popularly, this approach is attributed or credited to the works of E. Buckingham, and most of this work was done in 1914. Now, the essence of the work is something like this. Suppose you have a cylinder of diameter d exposed to a flow field like this, and we have to find, and we have a functional relationship between the variables. So it is kind of common sense to establish or to at least understand that the drag force, in this case R, would be a function of some of these variables, such as the flow speed to which the cylinder is exposed to, the dimension of the cylinder, the density of the flow field. For example, if you have a flow of air at a given velocity and viscosity, and then you have flow of oil over the cylinder, where the density is much larger, viscosity is perhaps much larger as well. So the drag force would be expected to increase. Similarly, if the size of the cylinder is very high, perhaps the drag force will increase again. So there is a kind of a dependency between these variables and the drag force. Okay, so one can speculate. Essentially, it's a you have some physical argument. It's a scientific speculation that the force of drag indicated by R here would depend on these independent variables v infinity, d, rho infinity, mu infinity, etc. So essentially, we can see that we have 4 independent variables in this simple problem. Of course, I should draw your attention because now that you have gone through the physics of drag in quite some detail. So drag on the cylinder is composed of skin friction drag, pressure drag due to flow separation, wave drag, etc. However, in this particular problem, we are staying in a region where we don't have to worry about wave drag. Okay, so we just are limited to profile drag composed of skin friction drag, pressure drag due to flow separation. And there we are saying that the drag force R is a function of these variables v infinity, d, rho infinity, mu infinity, etc. Of course, if you want to model it in a more critical way, you might add more independent variables. For example, surface roughness can come into the problem. Temperature of the flow field can come into the problem. And when you have more and more parameters, you will get more and more pi groups potentially. Now here in this problem, we have 4 independent variables. Now, one of the big advantages of using this Buckingham's Pi theorem approach is to reduce the footprint of your experimental data set that you might have to perform otherwise. For example, suppose I give this task to a person, and this person runs all these sets of experiments where, first of all, as you can see here, he's plotting the drag force versus the diameter of the cylinder. And of course, we have to be unbiased towards the density and the viscosity. So essentially, we need data set where eventually we can kind of figure out what would be the drag on a cylinder of this diameter when it is put in glycerin that has this density and this viscosity. So essentially, I'm saying that once you do this experiment, it will be nice to have some data from which we can answer all these questions, right? So you do the experiment, you collect your data set, and then from that data set, I should be able to say, what is the drag on a cylinder of this diameter exposed to a fluid of this density, this viscosity, this velocity, etc. So typically, what one would do is, so if you are not, going by the dimensional analysis approach, so there, what will happen is, one can expect that the data set would look something like, you plot the drag force versus say the diameter of the cylinder. So you measure the drag force on cylinders of various diameters. You hold the density and viscosity constant, in this case at rho1, mu1. You run the tunnels. For example, you might be putting this one in a wind tunnel. You are running the wind tunnel at 10 different velocities. And then at each, for a given velocity, say v1, suppose you have 10 different diameters. So you are measuring the drag force on the cylinder. So essentially, you get 10 points for each of these velocity fields. So 1, 2, 3, 4, 5, 6, 7, say 8, 9, and 10. So for every velocity that you choose, you vary your diameter of your cylinder. You get 10 data points for each velocity, and then there are 10 velocities here. So you have 100 data points for this particular problem. Now you change your mu to mu2, mu3, mu4, holding rho1 constant. So then you get 100 data points for each of these experiments. So in between you have, see in this row you have 10 different experiments. Again here, for a given mu1, you hold the mu1 constant, you vary rho. So then you have experiments for rho2 mu1, rho3 mu1, eventually rho10 mu1. So there also you have all these 100 data points. Here also you have 100 data points. So you have 100 plots, each plot with 100 data points. Okay, so it is easy to see that each of these plots has 100 data points. So you are varying diameter from this to this in increments. So over 10 increments. And then you are varying the velocity of the tunnel from v1 to v10. So for each of these velocity lines, you have 10 data points. So overall, from one plot, you have 100 data points. Now, if you cover the entire footprint, so essentially from row 1 to row 10, mu1 to mu10, you can show that essentially you are generating 100 plots. Okay, so you are generating 100 plots with 100 data points each. So it is you are essentially ending up collecting so many data points. Okay, now this is quite messy, and the worst news is, suppose when you come back and we are trying to use this data set to find, say, the drag force for a certain diameter for a rho or mu that doesn't exactly lie on these data sets. Okay, so suppose you are using some rho that does not belong to this, does not belong to this data set. So I'm interested in finding, so you give me these results and I'm now trying to use these results to find the drag on a cylinder of a given diameter among the range that we have. But the fluid has a density that is not within this range. And not only within this range, it could be somewhere between rho 1 and rho 2, but it is not exactly rho 1 or rho 2 or rho 3 or rho 10. Similarly, it can so happen that mu is also something that does not belong to this set. So when I say this set, it means mu can be somewhere out of this range, or mu can be somewhere in between two of these numbers, but not exactly any of these densities. So what will happen is, after having done so many tests, you come with a result that is not very useful when it comes to extrapolating or finding what would be the drag on a cylinder where your rho and mu are not matching with these experiments that you have done. Or you can have rho and mu are matching, but your velocities are not matching. Okay, maybe I need to find drag for this rho 1 and mu, but my velocity is somewhere here. So now you can say, okay, I have this data, I have this data, but exactly, we have this data, but we don't have this one. So you see that with so much effort, unless you are lucky enough that the requirement is such that it exactly falls on, one of these plots that you have, so 100 plots, and somehow the requirements are falling on these data points that you have taken, your this enormous amount of effort is actually quite useless. So we say 100 plots, so 100 into 100 data points, yet intermediate values are not available. Okay, so we will see that instead of these dimensional plots, if we plot it against the non-dimensional groups, something very interesting happens. And that will be one of the main reasons. So when you do experiments in aerodynamics or fluids, these non-dimensional group topic is often introduced before you start your experiments, because if you do not know the the dimensional analysis aspect, you might end up in this kind of an experiment, okay, where you report these dimensional parameters against each other with holding this constant, varying that. But eventually, after a lot of experimental work and effort, you will see that it's difficult to actually extrapolate or interpolate your data to find answers to problems that we have that do not exactly match with that experimental conditions under which you ran your tests. So for that, we come to Buckingham's Pi theorem, where we will see that starting from a problem such as, so this is the dimensional problem where R, the drag force, is a function of these independent variables. We can apply the Pi theorem to this above thing and get something of the form pi1 is a function of pi2. Now this f, wherever you see f, f subscript, just think of it as a function. It is not the same function. So in this particular case, all we are saying is this non-dimensional group pi1 is a function of this non-dimensional group pi2. And it can be shown from that Buckingham's Pi theorem analysis that pi1 is nothing but the drag force divided by rho v squared d square, where d is the diameter of the cylinder. And this is, we are familiar with it, it is some sort of a drag coefficient. On the other hand, this pi2 is nothing but the Reynolds number for the problem. So this is Reynolds number for the problem, and this falls out of Buckingham's Pi theorem approach. So we see that by applying Buckingham's Pi theorem from the dimensional problem, where drag is a function of velocity, diameter, density, viscosity, we from this problem where we have 4 independent variables, we have moved to this problem that just has 1 independent variable. Okay, so this is a very powerful reduction tool in the amount of experimental effort that you would otherwise have to do. So here, when you have a problem like this, what you do is you vary one of the independent variables and see the effect on the dependent variable while holding these other variables constant. So you vary one of these parameters, or rather, if I use the terms a little more strictly, you vary one of the variables, you hold the other variables as parameters, and then you see the dependence of the dependent variable on this independent variable for a given set of parameters that are being held constant for that particular experiment. Again, you can vary these parameters and then again test the effect of the independent variable on the dependent variable. Again, for some experiments, you might be holding, you might be varying v infinity while holding these as your constants. So, but it is again, as we have seen, it leads to a lot of experimental work, and that the hard work is not very useful because interpolating, extrapolating is not always possible. On the other hand, from Buckingham's Pi theorem, we haven't seen what it is or how it is applied. We can reduce this problem to one where you have, so you have only one independent variable and one dependent variable. So in your experiments, you can vary parameters, which in turn varies this independent variable, and then you measure the drag force, but instead of just plotting against drag force, you plot against r by rho v square d square. If you see, these are dimensionless. Okay, it is essentially force divided by the product of all these things, which also have the dimension of force. Similarly, this one has the dimension of viscosity by viscosity, so no dimension on the right hand side. So question is then, how do you find pi1, pi2? What if pi1 is a function of more than? So here we see pi1 is a function of pi2. So essentially we have two pi groups, so one becomes a function of the other. Buckingham's Pi theorem does not, unfortunately, give us the nature of this dependence. Okay, so that is to be found experimentally. So Buckingham's Pi theorem will give you all these pi groups, but the nature of dependence or the functional relation between these pi groups will not be given by Buckingham's Pi theorem. Okay, Buckingham's Pi theorem will just give you the non-dimensional groups. In some cases, these non-dimensional groups will be physically relevant groups like the Reynolds number, Mach number, but there is no guarantee for that. It will be a non-dimensional group. Depending on the choice of repeating variables, etc., you might get things that are physically relevant like Reynolds number, Mach number, Prandtl number. Depends on the problem where you are applying Buckingham's Pi theorem to. But again, it can be shown that these non-dimensional parameters can be, raised to powers, can be manipulated among each other to give you physically relevant non-dimensional parameters. So nonetheless, for this particular problem, for this the drag versus this, we see that it is possible to relate, to go from this problem of 5 variables, 4 independent variable, 1 dependent variable, to a problem where you have 1 independent variable and 1 dependent variable. So pi1 is a function of pi2, but in some cases, essentially where you have a lot of independent variables, you might end up with pi1 is a function of pi2, pi3, pi4, pi5. Okay, it will be simpler than the problem with dimensional parameters, but yet it might be such that you have more pi groups than just 2. And then you will see that there are some very important problems that has only 1 pi group, so we will briefly touch upon those as well. So you see that instead of plotting this In the previous plot you saw, we were plotting this drag force versus d for various velocities, and then while holding the densities and the viscosity constant. So we were, first we held this constant, changed the velocity from v1 to v10, changed the diameter from d1 to d10, and then we got, those 100 data points for each of these um, density and viscosity values. So we ended up with a big test matrix, or a big chunk of test data. On the other hand, if we plotted this drag coefficient versus Reynolds number, so essentially pi1 and pi2, what would have happened is your these values would have actually collapsed along this line. I mean, again, we are not really focusing on how the line will be. So this is just like a very hand waving way of saying that there will be some functional relationship between these two pi groups, and the data points from various experiments will actually collapse on this functional relationship line. Okay, so you see that by changing your, from test to test, your rho v infinity d can vary, your r will vary, so you calculate this number. Similarly, from experiment to experiment, your rho will vary, u will be different, diameter of the cylinder can vary, mu can vary. But then when you plot this value versus this value from different experiments, you will see that the data is actually collapsing around some functional relationship line. That is the power of this approach. So later on, if someone wants to find what is the drag force on a certain viscosity, certain diameter, certain density fluid, etc., you can actually input those things and get some value, and then from there you can get the, so from the non-dimensional value you can extract the dimensional values. So essentially, if I give you, so this is the data set, suppose, that has been generated through a similar kind of experiment that we have performed just before, but instead of plotting these things against the drag force versus diameter for various velocities while changing density and viscosity, we are running a test where we are doing the same things, but instead of plotting the dimensional variables, we are now plotting the non-dimensional variables that we obtained from Buckingham's Pi theorem approach. So we will see some line like this. Depends on the functional relationship between these two pi groups. I must emphasize again that this functional relationship is obtained experimentally. But the pi theorem doesn't tell us or give us any insight into what would be the functional relationship between these non-dimensional groups when you run an experiment and get these plots. Now you come with this, you give this plot to someone, and now they need to find what is the, say, the drag force on a cylinder of a certain d, in a certain v infinity, rho infinity, u infinity, mu infinity. So what they would do is they would plug in these numbers for their particular requirement, plug in. So they will, this number will give you some value here, and then you can figure out what is this value, and then by inserting rho, v infinity, and d, you can figure out what is the drag force. So then you see that you don't have this problem of that extrapolation, interpolation, or problem where the variables are not matching with your text conditions. Okay, so you can still get useful results once you have this condensed data set. Now we will get into the discussion of how do you find this pi1, pi2, etc. Okay, so how do you find pi1, pi2? Essentially, pi1, pi2, pi3, pi4, depending on the number of dimensional variables you have and the number of fundamental dimensions that are there in the problem. You can see there is a way to find the number of non-dimensional groups. It's somewhat based on the matrix algebra, the rank and order of matrices, and that gives you the number of these non-dimensional groups that will come out of a given problem. So question is, how do you find pi1, pi2? So here I'm saying, instead of plotting, drag force versus diameter, let us plot this pi1 versus pi2 for the problem. Question is, how do you find pi1, pi2? Now here, this is the recipe for how do you do that. So first of all, select the relevant variables. So, if you want to find the drag force on a cylinder, perhaps the relevant variables are the diameter of the cylinder, the free stream velocity, the free stream density, the viscosity of the flow, etc. So there are 4 independent variables and 1 dependent variable. So total we have 5 variables that are pertinent to this problem. Now again, it depends on the the detail at which you are operating. So for example, surface roughness can be included, temperature perhaps can be included, and then there are other things that can be included. And you will see that in those, if you start like that, you might end up with more pi groups. But nonetheless, this is one of the examples where that might help keep things a bit simple. And we will see or show that from this kind of a relationship of the dimensional parameters, one can end up in a relationship between the non-dimensional groups. Once again, we will see that these non-dimensional groups are not set in stone. Okay, it depends on the way you choose, or it depends on the details of your approach. It depends on your repeating variables. So we will show it here. So question is, so first you then answer, first you find the relevant variables and you form a functional relationship such as this. So then how many fundamental dimension quantities are involved? So when we talk about this fundamental dimensional quantity, we are talking about mass, length, time, temperature, and charge. So in this particular problem, if you think of the drag force, think of the diameter, the velocity, the density, viscosity, etc., you can show that if you look at this table, velocity essentially is L by T, length by time. Diameter, of course, is just length, L. The density is mass by volume, m by L cube, and similarly viscosity and your force is given by mass length by time square. So this way you can figure out the fundamental dimensions. Okay, so how many fundamental dimensional quantities are involved? So we have length, time, and mass. So we have 3 fundamental dimensional quantities are there. So n is equal to 3. So m is equal to 5, n is equal to 3. Buckingham's Pi theorem says that the functional relationship between m is equal to 5 physical variables involving n equals 3 fundamental dimensional quantities can be represented by a functional relationship between 2 non-dimensional groups or 2 pi groups. So if you have m is equal to 5, okay, so these are all the parameters or the dimensional parameters of the problem. And then you have fundamental dimensions that are involved in the problem is 3, then m minus n is equal to 2 gives you the number of the pi groups. So you will see that in this problem, there will be 2 pi groups that are relevant to the problem. Now you understand that if you had more variables that you brought into your model, you would have these other things coming into picture where, so your m, perhaps if you, for example, if you include surface roughness or if you include temperature, then your m is increasing. So you see that m minus n is increasing. And of course, given that n is still like MLT in a lot of physical problems, actually it is MLT. However, you have to still keep in mind that essentially you have to make a check of mass, length, time, temperature, charge, etc. However many fundamental dimensions you are having, or fundamental dimensional quantities you are are involved in the problem. So in this case, we see that we will have 2 non-dimensional groups. So given something like this or something like this, given a relationship like this or a relationship like this, where we move dependent on one side, independent on the other side, we seek something of this form. Okay, so in this particular case, because we just have Buckingham's Pi theorem indicated that we just have this Buckingham's Pi theorem showed us that we have 2 pi groups. Okay, so now from Buckingham's Pi theorem approach, so we see this thing and we get for this particular problem. Okay, so it will vary from problem to problem depending on how many relevant variables are there. So how many m and how many n. And we see that for this particular problem, we have 2 non-dimensional variables. Now this is the important step. Now you choose three variables from these independent set. So from these independent variables, you choose three variables as the repeating variables. And there are some rules by which your repeating variables should be chosen. The repeating variables should be such that among them they have all the dimensions or the fundamental dimensions. So essentially, MLT should be there in your choice of these repeating variables. Okay, you should not choose repeating variables where say time is left out. In this case, for example, we are choosing rho, v, and d as repeating variables, and you can convince yourself. So if you have rho, v, and d, so m, l is there, l is there, and l by t, t is there. So you see m, l, t, all the fundamental dimensional quantities are there in this choice of repeating variables. However, if you chose some other three, it seems that here choosing any three would almost lead to the satisfaction that all these fundamental dimensional quantities will be there. But suppose in a problem you have all these, but you have m by l cube and m by l square, and we choose m by l cube, m by l square, and l, and t is somehow left out. So we cannot choose them as the repeating variables. So anyway, here we see that we have to choose three variables from these independent variables as repeating variables. And then we will bring in these. So essentially, you can see that rho, v, and d have been chosen as repeating variables. And then we will bring in the variables that are left out one by one. Okay, so you see that here we have, so we bring in three repeating variables because n is 3. We bring in the variables that are left out. So once you bring, say, rho vd, so if you bring rho, so if you make these three as your repeating variables, then you are left out with this and this. So what you do is you say pi1 is equal to the repeating variables raised to powers a, b, c multiplied by r. Pi2 is again rho vd raised to some powers into mu. Now, since the dimension of these pi groups is, or rather, since these pi groups are non-dimensional, what will happen is these right-hand sides, the powers have to satisfy some algebraic constraints so that the powers of the right-hand side arrange themselves in such a way that they become non-dimensional as well. So if you think of this first expression, so pi1, so we have the repeating variables, we raise them to appropriate powers ABC, we don't know what they are, but that will come from the constraint that this one has no dimension. Okay, so what will happen is, so the dimension of this is nothing but m by l cube to the power a. So density is m by l cube, so m by l cube to the power a. Velocity is L by t, length by time, distance by time, in this case to the power b. The diameter of the cylinder is L, so raised to the power c is L to the power c. And then the drag force R is nothing but ml by t square, okay, raised to the power 1. So what we can say is this right hand side has dimensions of mass to the power a plus 1, length to the power minus 3a plus b plus c plus 1, and time to the power minus b minus 2. Of course, the pi group is dimensionless, so all my powers should actually go to 0 so that my left hand side becomes, so that the dimensional agreement is there between the left hand side and the right hand side. So now what will happen is you see that a plus 1 becomes 0. A plus 1 has to be made 0 so that pi1 has no flavor of mass. Minus 3a plus b plus c plus 1 has to be 0, so my pi1 has no flavor of length. And similarly, minus b minus 2 has to be 0, so that my pi1 has no flavor of time. Okay, so because it has no dimensions, dimensionless quantity. So essentially, when you it just has a numeric value, but it doesn't have any dimension. Okay, so no length dimension or time dimension or mass dimension in this particular problem. So once you have these algebraic relationships, you can find the values of a, b, and c, and thereby you can find the value of pi1. Okay, so then pi1 will have a numeric value, but it will not have a kilogram or seconds or like the meters as well, so mass, length, and time. So your pi1 ends up becoming something like this. Okay, so if you plug in the values of a, b, and c that you find from here, you will see that pi1 becomes r divided by rho infinity v infinity square times d square. Okay, so similarly, pi1 becomes this. So pi1 is this. Pi2 is similarly by running the same kind of dimensional argument, or rather the non-dimensional argument. So essentially, if you look at this particular thing, so my repeating variables rho, v, and d raised to the power. So it doesn't really matter. D, E, F is just like three numbers. We could have again used A, B, C. All it matters is we plug in the dimensions of each of these variables, and then make sure that the algebra for the constraints on D, E, F, and all those things are such that pi2 becomes dimensionless. Okay, so no flavor of mass or time or length stays in pi2, and the way to do it is set the coefficients to 0. So similarly, this is what we have done here. So how to find pi2? The dimension of pi2 is something like this, but the dimension of pi2 is has nothing to do with mass, length, or time. So these powers should then become 0. And when we set them to 0, we get these values. So pi2 then becomes mu infinity divided by rho infinity, v infinity, and d. Now we will see that if pi1 or pi2 is non-dimensional in the way that we see here, the reciprocal or a power of it or a combination of these pi1, pi2s in various ways would also be non-dimensional groups. Because once you have if you have something which is non-dimensional, taking the reciprocal of it, raising it to a power, those things are also non-dimensional, right? Because dimension will not creep in. So if you just have a number, suddenly it will not become kilograms or meters or seconds or a combination of those things. So the idea is if you have mu1 and mu2, sorry, pi1 and pi2, then like you can plot pi1 versus pi2 for the experiment, but you can also do 1 by pi1 versus pi2. You can do pi1 square versus pi2. You can also get new non-dimensional variables by combining appropriate powers of pi1, pi2. Now, why we do that? Because sometimes, depending on the choice of these repeating variables, you might find non-dimensional groups that do not have physical relevance. It's still there is inbuilt physical relevance because it's a non-dimensional group, but it is not one of those commonly used physically insightful non-dimensional parameter like Reynolds number, Mach number, Prandtl number, or even like simple things like the drag coefficient or force lift coefficient, etc. So to get your the non-dimensional parameters in those forms, sometimes some manipulation of these pi1, pi2, etc. that you get from a random choice of repeating variables. Some manipulations have to be done that way. Okay, so here my pi2 is this. Now pi2 can be the reciprocal of above. So we, instead of plotting this versus mu by rho vd, we can just replace pi. We can take pi2 as like 1 by pi2, because it still is a non-dimensional parameter, and we will see that this has this very important name, which is known as Reynolds number. And you will see that there's something called inertia force by viscous force, and that is where that some non-dimensional parameters have some physical sense. Some non-dimensional parameters, although it will still give you that advantage of data collapsing on one functional line, etc. But it may not have physical significance in the way we interpret things. So there sometimes you might have to combine or take powers or reciprocals, etc. So here you see it is one example where our choice of repeating variables gave us one pi group that was the reciprocal of this popularly known non-dimensional group known as Reynolds number. So what we said is instead of plotting versus pi2 like this, we can just plot against this. Okay, so that is Reynolds number. So raising two powers does not change non-dimensional behavior of pi terms. You can multiply pi terms raised to powers to get new pi terms. Our interest is in plotting against Reynolds number, Mach number, CD, CL, CN, etc. So some rearranging can be needed. Now, instead of choosing rho infinity, V infinity, and D as repeating variables, so you see that in this case, we have chosen rho infinity, V infinity, and D as the repeating variables. So I'm saying that if you do not choose them as the repeating variables, what if we choose, say, V, D, and mu as the repeating variables? So instead of choosing rho V, D, instead of choosing rho V and D as the repeating variables, what if we choose V, D, and mu? So V, D, and mu as the repeating variables. Okay, so in this particular problem, we have chosen rho. We have chosen rho V and D as the repeating variables. Rho D and D as the repeating variables, and we got pi1, pi2, which are so we got the drag coefficient and 1 by Reynolds number, but we plotted against Reynolds number. The plots will be, the plot will change if you plot against Reynolds number or 1 by Reynolds number. Of course, they will not be the same plot, but at least we got from the choice of rho V and D, we got pi1, which was directly, the non-dimensionalized force, or the force coefficient or drag coefficient in this particular case, and we got Reynolds number or 1 by Reynolds number. However, the question is what happens instead of D, V, and rho choice as repeating variables, we choose D, V, and mu. Now, first of all, let us see whether they satisfy D, the dimension requirement, that is, they contain all the dimensions or all the fundamental dimensional quantities. So D has length. Sorry, let me switch to blue. Okay, so D has L, V has L and T, so we have L and T taken care of. Left is M, so our last choice should be, okay, D and V. Mu should have mass. Okay, so we see mu has mass, so it is a valid choice of repeating variables. Now, when we take that, you see that your mu1 comes to be R by mu infinity, V infinity, D, whereas pi2 goes rho V D by mu, so which is Reynolds number. So you see here, we don't even have to take the reciprocal. So pi2 directly becomes the Reynolds number. But this pi1 is not something that is a non-dimensional group with physical significance. Now, I should not really say like that. It is perhaps there is physical significance, but it's not one of those popularly known non-dimensional parameters with physical significance. So, but you can still, run the experiment, plot this against this. You still have that advantage of small amount of experiment generating data that can be extrapolated or interpolated to get, what would be the drag force on a cylinder, of a certain diameter in a fluid of a certain rho and mu, which do not fall exactly on, your test points. So you still have that advantage, but that physical insight of how things vary with these physically relevant non-dimensional parameters will not be there. And of course, this line will be different from whatever you get from here. But nonetheless, the data collapse and all those things are similar, and they, bear the same advantage as we have seen. So someone who doesn't have an idea of this Buckingham's Pi theorem or the dimensional analysis and similitude thing, they might end up running experiments and reporting a lot of these dimensional variables contrast against some other dimensional variable holding some dimensional variables constant, and that would lead to a huge amount of effort and with difficulty in interpolation or interpolating or extrapolating data. On the other hand, with Buckingham's Pi theorem approach, you can figure out the non-dimensional groups, and when you plot them, there is this advantage that since the data has this beautiful collapse on these lines that define the functional relationship between the pi groups, you have a great amount of advantage in interpolating and extrapolating data required for your configurations that do not fall exactly on the things with which you have tested. Now, a very famous use of these Buckingham's Pi theorem is attributed or was done by G.I. Taylor in 1950. You remember that in the end of the World War, the atom bomb explosions in Japan. There was some curiosity about the energy deposited by these atomic explosions that created the blast wave. When we study compressible flow, or when we study high temperature gas dynamics or unsteady shock waves, etc., we will perhaps get into the discussion of explosion with the idea of explosion safety honestly in mind. We would rather focus our attention on how to create a safe working environment where an explosion can happen. Industrial processes often create situations where you might have an explosion, and it might be important to understand the physics of the blast wave that is generated by the explosion, the distance through which it travels, at what strength, what kind of impact it has on things that come in its path, etc. G.I. Taylor's interest was in finding out the energy that was deposited by these nuclear atomic explosions, and so he made a classic use of this approach. So once again, you form a working relationship between the parameters of the problem. So in this case, the radius of the shock or the blast wave at a given point in time could be expected to be a function of the energy deposited, the time at which we are looking at RS, and the density of the ambient medium. Okay, so rho naught. So here we can see that we have 4 physical variables and 3 fundamental dimensions. So you can see that if you work out the dimensions of each of them, this is m by L cube density. Radius is, so RS is you can think of it as the distance of the front of the shock front or the blast wave front from the origin of the blast wave, or where the energy is deposited, the zone of impact or the explosion. And then eta naught is the energy that is being released, that has been released, and we assume instantaneous release of energy. Although it can happen over a small instant of time, you can still model it as instantaneous. Now this one is an unsteady problem. Okay, if you really want to solve this problem from first principles, essentially apply continuity, momentum, energy equations, it is an unsteady shock wave problem, and it can get quite messy. On the other hand, what one can do is, you have in this problem we have 4 physical variables, 3 fundamental dimensions we saw from here, m, L and T are there. So then we choose 3 repeating variables because we have 3 fundamental dimensions. So let us say we chose RS, eta naught, and rho naught, and then what happens is whatever is not there, we bring that in. So again, similar thing. So RS, eta naught, rho naught to the powers ABC, and then just bring the left out parameter in. In this case, you see that we have done it in a slightly different way. We have raised, so we have kept RS without any power. We have put some powers on eta naught, rho naught, and T. Essentially, it doesn't really matter. All it matters is these coefficients should be chosen such that the right hand side becomes the dimensional thing goes to 0. Okay, so if you again do the similar MLT raised to the powers of the combinations of A, B, C, and some numerics, you can show that pi 1 is nothing but. Okay, so this is from the similar kind of thing that we did here. Okay, so you say this thing, then you apply, then you look at the dimensions of the pi group and the dimensions of the right hand side, and then work out the algebra so that the dimension of the right hand side goes to 0, and it goes to 0 when these constraints on A, B, and C are satisfied. Okay, and that will give you the values of A, B, and C. So here, like if you go back to this one, so here also by using something like that, you get that pi1 is something like this. Now the question is, how do we get the value of pi1? So here, I think anecdotally, there were 2 clock towers, and that had stopped at when the blast wave passed through those locations, and so essentially, if you know the time and the distance rs, so essentially you know that interval between the time in which so the clock tower stopped when the wave kind of reached those clock towers. So by using the time difference and the rs difference, your pi1 could be calculated, and that gives you the functional relationship between rs as a function of these other variables. And of course, if you do, since you have rs versus time, you can get rs dot or velocity, etc. A similar problem also is there for the simple pendulum, where we say that the time period has to do something with the mass of the pendulum, the length of the pendulum, the acceleration due to gravity, etc. And we see that, so here we have 4 physical variables with 3 fundamental dimensions, and following the approach like this, we can show that your time period is the pi group, so let us call it pi1. Okay, so pi1 times this, and from experiments it can be shown that t is equal to, so this pi is the pi 3.14 thing, whereas this pi1 is just a notation for the pi group. Okay, so this is just, we call it a pi group, you can just call it a non-dimensional group, and from experiment, so dimensional analysis leads us up to this point, t is equal to pi1 times this, and then from experiments it can be shown that okay, t is equal to 2 pi square root of L by G. So these are problems with 1 pi group. Now for us, I think the more pertinent problem is, for example, the force on airfoil. You see, so R, remember we can take the component along the relative wind and the perpendicular to the relative wind and get L and drag. So the force on this wing or airfoil cross section can be thought of as a function of the v infinity, rho infinity, chord length, mu infinity, speed of sound, etc. So again, as I said, that it depends on what parameters you think are relevant to the problem, and this can also be written as just, you can either split it in the dependent independent variable fashion, which is a little bit more like it puts a little bit of physical sense into the problem. On the other hand, you can think of it as a mathematical problem and just put a functional relationship such as this. If you do it like this, then that emphasis on what is independent, what is dependent is kind of lost. But nonetheless, it will lead you to similar kind of result. So here we have 6 physical variables. You run the dimension for each of these variables, and you see that there are 3 fundamental dimensional quantities, M, L, and T. So Buckingham Pi theorem says that we should seek to represent the functional relationship between 6 physical variables with 3 fundamental dimensional groups in 6 minus 3 or 3 pi groups. So this whole problem can be recast. So this problem can be cast into a relationship between 3 pi groups. Okay, so remember that the drag on the cylinder was a problem where we had 2 pi groups. The blast wave problem, the pendulum time problem, where we had 1 pi group, and this one is a problem where we have 3 pi groups. And once again, it depends on that m and n, how many parameters in the physical problem, how many fundamental physical dimensions are involved in the problem, and the difference gives you the number of pi groups. Here again, we choose rho, v infinity, and c as repeating variables, and we work out these things in a similar fashion. You remember the algebra form. We set the dimensions on both sides equal to 0, and then we solve them, and we get some insight into what is pi 1, pi 2, and pi 3. So we will end up today's discussion here. We are ending the time limit for this class. We will continue with the Buckingham's Pi theorem in the next lecture, and then we will get into discussion of other things. Thank you very much for your time, and see you in the next class.